All right, everyone. Welcome back for the afternoon. Now we have, as prelude to Alex Smith's first talk, we have Tristan Phillips from Dartmouth talking about the BSD conjecture.
Yeah, thank you. I'd really like to thank Jen for making me aware of this workshop and for the organizers for giving me this opportunity to give a talk here. I really appreciate it. So I'll be talking about the Birch and Swinnerton-Dyer conjecture, and this talk will be more focused on motivation maybe than it is on technical detail. Okay. So I think of number theory as being something along the lines of studying integers. And depending on how much you agree or disagree with this statement, you can make these squiggles bigger squiggly or straighter squiggly. But vaguely, I think most of us like to think of number theory as being some sort of study of the whole numbers. And I sometimes ask myself, like I spend a lot of time thinking about a big curve, like what sort of things are these actually telling us about the whole numbers? And so much of the talk is going to be kind of motivating it from this basic viewpoint of number theory to begin with. And kind of the first thing I'd like to point out is that questions about integers can often be transformed into questions about solutions to equations. So what they polynomial equation. These are often called Diophantine equations. And what better place to start than an example that can be found in Diophantus's arithmetica. So this goes back a long time ago, approximately 250 the year 250, back when years were 3 digits. And so what did Diophantus ask? Well, he had this question. Or I don't know, I don't think it was stated as a question, maybe a challenge. So divide a given number into 2 numbers but that their product is a cube minus its side. So this is a question presumably about the integers. When he says number here, it should be an integer. We can kind of transform it. You can transform it into a Diophantine equation. So no question about finding any integer solutions to equations. And so here, the question could be rephrased as we're trying to, so given an integer a, does there exist rational numbers x and y, so that the equation y times a minus y equals x cubed minus x. And so in his book, Diophantus gives an example when a equals 6. He shows that you can find the solution 17/9 and 26/27. So somehow he comes up with this solution. So that's one example. The second example I want to mention goes back even before Diophantus. It's the question of which right triangles have integer side lengths. So this can be written as a Diophantine equation using the Pythagorean theorem. So to find all triples, and equivalently, if you say assume z is non-zero and divide through by z squared, you can write this as finding pairs of rational numbers. Still I the unit circle. That's the second question. The third question is also about right triangles. And that is, what integers can be realized as areas of right triangles with rational side length? So just as an example, if we look at the following triangle, and if you find its area, you'll see that the area is 7, and therefore 7 is what we call a congruent number. So numbers with this property are congruent numbers. So that's maybe a positive example. The negative example is 1. So for Vermont, using his method of descent, that 1 is not congruent. there does not equal such a right triangle with rational side lengths whose area is 1. And a nice application of this, or corollary of this, is that if you look at any square, for example, 3025, well, then it also cannot be congruent. Because if it were, then you could just rescale and get something of area 1. Okay. So I've given a couple of examples, but I haven't described what the X-19 equation is. Um, And just one other maybe important example. So we talked a little bit about Fermat, and there's also, of course, Fermat's last theorem. So hopefully you're convinced that there's a lot of interesting number theoretic questions that can be rephrased in terms of finding solutions to polynomial equations. And so we might want to study more generally the problem of finding rational solutions to polynomials. But there's a lot of polynomials. You might want to focus on different classes at different times. And the first class I want to discuss is the class of polynomials in one variable. With polynomials in one variable, we know by the fundamental theorem of algebra that they'll be at most the degree of the polynomial number of rational solutions, and oftentimes there will be less. And there's a good method for actually determining all the rational roots or all the rational solutions. So there's the rational root theorem. So let f of x be a polynomial in one variable. Let's say with integer coefficients. We'll also assume that the constant term and the leading coefficient are non-zero. Any rational solution to f of x equals 0 is of the form a over b, where you write this in lowest terms, of course, and then you have and then you also know that that a divides c naught and b divides Pn. Okay. And so there'll only be finitely many rational numbers. You can plug them in and see exactly what they are. So we understand how to solve polynomials in one variable, but things all of a sudden get much more difficult when you move on to two variables. So what happens in two variables? So in two variables, we're going to stratify further by looking at the degrees. So we'll start with degree 1. Okay, so these are just linear equations. So they look something like this. And this can be solved using algebra. So you can say high school algebra. The solutions are will be of the form s comma negative b s of c over a, where s is some varying rational number. So far, so easy. But what happens when we increase the degree? So now we have two variables, and instead of degree 1, we'll have degree 2. So as a first example, to look at the polynomial x squared plus y squared is 3. And it turns out now, if you look at the equation f equals 0, it doesn't have any rational solution. Now let's look at another example from one of the motivating problems. So motivated by looking for Pythagorean triples, we're kind of classifying right triangles with full number side lengths. We saw this equation, the unit circle, show up. And so what can we say about rational points on the unit circle? perspective. Okay, so there's some obvious points on this circle, so at least we're not in this case where there are none. For example, we have the point -1, 0. But we're interested maybe in other rational points. So here, suppose we have just some rational point on this circle. So here's a rational point. And let's consider the line passing through these 2 points. Then this line will have a rational slope, because both the points have just rational coordinates. And therefore it's going to intersect the rational line, the rational vertical line, at another point that will also be a rational. This point has x coordinate 0 and y coordinate, let's say s. And it turns out that you can play this the other way, where instead if I pick some kind of rational point on the y-axis and I draw a line, it will have a rational slope and it will intersect the unit circle at a rational point. And in fact, you get all rational points this on the unit circle this way, except for the point you started with, which you can kind of think of as being the line, kind of the vertical line with infinite slope. But I believe this goes back maybe to Euclid. Between there's a bijection between slopes, these rational lines, and rational solutions. To x squared plus y squared. And with a bit of work, you can make this precise. Also, if you like projective space, you can think of this as kind of being the rational points on the projective line. And so here, what am I doing? I'm taking a slope, and with a bit of algebra, you can show that it maps to this point on the unit circle. And then this actually allows us to answer the question about what right triangles have integer side lengths. So again, a little bit of work is required, but you can actually find that every triangle with integer side length is similar to one of this form. So here m and n are some integers. So now we have these kind of two cases, these two situations. We have one situation where we didn't have any solution. We have this other situation where there's infinitely many solutions, and we have this kind of rational parameterization of them. And it turns out those are the only two things that can happen in this. And moreover, there's a effective way to determine which of these cases you're in. So whether there's no solutions or if there's infinitely many. And this is the Hasse-Minkowski theorem. Yeah, so Hasse-Minkowski say that you can test which case you're in by just seeing whether it has a solution over all the completions, over the real numbers in QP for all P. And in fact, you only have to check finitely many. So it really is an effective way of figuring out which case you're in. So that's the story in kind of degree 2. Are there any questions about anything so far? So we still have our polynomials in 2 variables. We've done degree 1, we've done degree 2. How far could degree 3 be? So again, we'll start with a couple of examples like we did in the degree 2 case. So here's an example. Good summer. Okay, so we have this cubic polynomial, and it turns out that if you equate it with 0, it doesn't have any rational solutions. And what's significant about this example is if we think back to this, we might hope to have a Hasse-Minkowski theorem also for degree 3, but in fact, you can show it's possible to show that this has solutions over QP for all P as well as a real solution. And so this is an example showing that the Hasse principle fails for the degree 3 case. And I should also remark that there are easier examples to show that there are qubits with no rational solution. Okay, another example. So in this case, there is exactly 2 rational solutions. Maybe I'll leave it for you guys to find. They're not so difficult to find. Maybe the hint here is that essentially we're looking for solutions to this equation. So one is kind of the product of consecutive integers a cube, and that can't happen very often. Okay, so let's return to Diophantus's example. So he was interested in essentially this polynomial of degree 3. And somehow he found this crazy solution, whatever it was. So it was 2.9. So he went about doing this in a very algebraic way. But you can kind of reformulate it, what he did in a more geometric way. And so that's what I'm going to do. So if you kind of graph f of x equals 0, it looks something like this. And one way to think about what he did is he found kind of a trivial solution. So presumably he wanted non-trivial solutions to this, but he first noted that there's this trivial solution at -1, and then he did essentially the algebraic version of looking at a tangent line. And the nice thing about this is that you have a double root, and you have a cubic. And so when you go to solve things, it turns out that you have a cubic where you know two of the roots, and then the third root's going to be linear, and you can find that it is also a rational point. And that rational point is exactly the point that he gives the solution. But is this the only solution? So if you were just thinking about this, you might be like, well, we could try playing the game again. Maybe we take a tangent line here. We can't kind of take these 2 points and draw a line through them and get anything new. But another thing you might do is that there's a lot of symmetry here. So you can also look at, if we kind of flip this, so this is symmetric about the line y=3, and we can flip it and get a new solution. So if we kind of flip it across this line, we get another point. So it'll have the same x-axis. And it'll have the same x value, but not the y value. And now we can play the game again with the first point, it's -1, point. And since it's a cubic, it should intersect, a line should intersect in 3 places. So we somehow get a new point. And if you work out the coordinates of that point, and kind of continuing to play games like this, where you reflect and you draw lines through 2 points to find new rational points on the original curve, you can actually show using elementary methods that there are infinitely many solutions to this. Birch. Infinitely many rational solutions. Okay. So where are we in the degree 3 case? We have infinitely many, we have finitely many, we have none. So it's very hard to know. And the remarkable thing is that the Birch and Swinnerton-Dyer conjecture gives some way of determining whether we're in the case where there's finitely many solutions or the case of infinitely many solutions. So that's a pretty remarkable result. In some ways, you might think, like, how is the Birch and Swinnerton-Dyer conjecture? Like, number theory is so old, and the Birch and Swinnerton-Dyer conjecture is relatively young compared to number theory. How could it be that it's so significant? And that is because it's not so clear how you would determine between these. So that's kind of, this first part of the talk is kind of been like about why the Birch and Swinnerton-Dyer conjecture, why compare. But now I guess we should slowly start moving towards what exactly the Birch and Swinnerton-Dyer conjecture is. The polynomial and 2 variables. defined the plane curve. And such a curve is smooth if there are no points where there's kind of like a sharp point or bend or self-intersection. But that's all. So homogenizing the equations gives you a projective curve. So now instead of kind of living in some affine space, we're kind of imagining it living in some projective space. And then an elliptic curve is a smooth projective Venus one algebraic curve with a specified point so over numbers. And it turns out that any elliptic curve over the rational numbers be written in this for Firehouse form. the non-zero discriminant. So kind of I think the first written example of an elliptic curve is this example of Diophantus, but it isn't written in the standard form. So if we are looking at the curve, if we're looking at this curve, then by subtracting 9 from each side, we aren't really changing the solution set at all. And by making a couple of changes of variables, so I'm going to send x to negative x and y to y plus 3. And after rearranging terms, you get something in the standard form. You get y squared equals x cubed minus x plus 4. So you could think about elliptic curves as just being this class of Diophantine equation of this form. But one of the remarkable things about elliptic curve is that they have a group law. So the way that kind of I drew in that example of Diophantus, well, now his elliptic curve looks a little bit more in this direction, not quite like this, but similar. And in general, this works. So if you have two rational points, call them A and B, then you can add them by taking a tangent line through them. You'll get a new point. But that's not actually A plus B. You have to take another line through this point and the point at infinity corresponding to the identity, and then you get the point A plus B. And so, like, I guess implicitly, Diophantus kind of saw this, but more explicitly, Newton thought about this sort of thing, but they weren't quite thinking about it as an addition law. I think in the late 1800s, Joule showed associativity, although he didn't use that language. And later, Poincaré kind of helped put things together. And so it turns out that the set of rational points is a group. This is proven around 1900. So it's not just a set, it actually has this group structure. And Poincaré asked, well, is this group finitely generated? One thing to note is that it's certainly abelian, because if I, instead of adding A plus B, I can add B plus A, and this you'll get the same thing. But is it finitely generated? And Mordell proved that that in fact was the case. So about 2 decades later, that it is finitely generated, and therefore it's a finitely generated abelian group. So it can be written as some finite torsion subgroup plus some free part of rank R. These are known as the working subgroup in the rank of the elliptic curve. Kind of remarkable work of Mather shows that there's only finitely many possibilities for the torsion subgroup of the rational number, and they're relatively small. So this thing can't get too out of hand. And so much of what is, pretty much everything that's determining whether or not this has infinitely many points, whether an elliptic curve has infinitely many points, is whether or not the rank is 0 or positive. Oh yeah. So a key example that we know what the rank is example slash I guess theorem is that an integer is congruent if and only if the elliptic curve has positive rank. So the Birch and Swinnerton-Dyer conjecture should somehow tell us something about this ring. And so I mentioned that the Hasse principle fails, but that doesn't mean that looking at reductions on modular primes isn't useful. We just have to be a little bit more. So if we look at solutions to an elliptic curve over a finite field, so suppose we're given an equation like this, maybe rescale so that a and b are integers to make things a little easier, and then consider this equation not over the rational numbers, but instead over a finite field. How many solutions would you expect it to have? Well, I can choose any value of x I want, so let me just choose some value of x. I'll get some number over here, and I'm asking, when is that number square? Well, we know over a finite field about half the numbers, exactly half the numbers are squares, half the non-zero numbers. And so you might think, well, maybe it's p over 2, but remember, each of those squares you have to count twice, because there's 2 square roots. And so you expect this to be somewhere in the ballpark of the prime p. However, if you have a positive rank, you have a large rank elliptic curve, you might think maybe that biases things. So when you take reductions, maybe there's a bit more points in general. And this is exactly kind of, I guess, the insight behind the Birch and Swinnerton-Dyer conjecture. The amazing thing is that you can actually kind of make this precise enough to make a precise conjecture. So there's also the monetary prize, if you can prove this, and the conjecture phrase explained with is that if you look at the product of these kind of counts over finite fields, you divide by p, then that should be growing on the order of log of x, the rank of the elliptic curve. So for example, if the rank is 0, then indeed this idea that the count should be around p is true. It should, like we expect it to be growing, or we expect it to be a constant, whereas if the rank is positive, then we should actually get that this is larger than p for a sufficiently number of p that we'll see some growth. You can kind of graph this out. I mean, you can graph this for an elliptic curve running through the primes, and you can kind of see how it's growing, and then based on how it's growing, you can make guesses about what the range should be. So, and a remarkable conjecture. But this isn't perhaps the way that the conjecture is typically stated. So to make it more fancy, let's first define the trace of Frobenius. So the discriminant kind of dictates what primes, when you reduce the elliptic curve modulo the prime, whether it still is an elliptic curve over the finite field. And so for a second, let's just avoid those primes, or really for the entire talk, we're going to avoid the bad primes. And then we have this thing called the trace of Frobenius, which we'll write as a sub b, and it's just kind of a shift of the number of points on the elliptic curve. And secretly, this is the expected number of points, not p, because if we're thinking of it as a projective curve, then there's some point at infinity. And then we're going to define the L function associated to the elliptic curve. So for x, the complex number, we'll first define these local L factors. So when so away from the bad primes, they'll look like this. Like 2 and all these to bad reduction. And there's other cases when at bad reduction, based on what type of reduction it is. Something else. And the L function of the elliptic curve is the product of these things over all primes. And this converges by work of Passa when the real part of S is greater than 3/2. This is due to Hassa based on things like the Hassa bound. And you might wonder, and Hassa wondered, this is, can you analytically continue the L functions of elliptic curves to the entire complex plane? So this was needed for certain elliptic curves in Wiles's proof of Fermat's last theorem. So he worked on this, and later a number of other authors completed it for all elliptic curves. This is eventually the modularity theorem. Gives you this. It and here's kind of maybe a more modern formulation of the Birch and Swinnerton-Dyer conjecture. So if you write out the Taylor expansion, of the L function at s equals 1, and it's conjectured will have leading, or I don't know what to call this, lowest term, that shape is an explicit constant in terms of invariance of the elliptic curve. Plus non-zero, but yes. Although it'd be quite interesting if you can ever show that it's zero. So one remark about this is that this conjecture was made well before this theorem. So in fact, the conjecture was made before it made sense. But it doesn't make sense to talk about the expansion at s equals 1 if you don't know this. And another comment is kind of hidden within this constant. There's the so-called Tate-Shafarevich group, and also implicit in this is that the Tate-Shafarevich group is finite, which is another open problem that's received a lot of attention. So I guess one thing to mention is that the analytic ring so what people call the analytic rank of the elliptic curve is the order of vanishing at s equals 1 of the L. So one form, the conjecture, be a slightly weaker form than what I just stated. The conjecture is that this analytic rank is the same as the actual rank of the elliptic curve for all elliptic curves. And maybe in just the last couple of minutes, I'll just quickly say in words what is known towards the conjecture. So just a couple words about that. The most significant kind of progress towards the conjecture, at least my opinion, has been the work of Gross-Zagier and Olivagen that have shown that if you assume the analytic rank is 0 or 1, in fact, you get that the actual rank is 0 or 1 correspondingly. And they also show that the Tate-Shafarevich group are finite in those cases. And then recently there's been some work on like the so-called p-converse of that, where you kind of try to go the opposite direction. If you assume the rank is 0 or 1, can you show that the analytic rank is 0 or 1? And so there's been a lot of progress there, but there's still some cases that are not known. But yeah, I think that's a good place to start.
Yeah.